Tonight, we're going to explore something that sounds like a simple number, but turns into one of the most brutal journeys a human being could attempt. 1 light year. You'd assume the hard part is speed, building an engine fast enough to get there. It isn't. The hard part is everything speed brings with it. Forces the human body was never built to handle, and a ship that has to survive conditions most engineering was never designed for either. And every one of those problems gets worse the longer the journey continues. By the end of tonight, you're going to understand exactly what 1 light year actually demands, and why the distance itself is only the beginning of the problem. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the number. 1 light year is 5.88 trillion miles. That is the distance light travels in a single year, moving at 186,000 miles per second. Nothing in nature moves faster than that. Not particles, not energy, not information. That speed is not a record waiting to be broken by better engineering. It is a hard boundary written into the structure of the universe itself. The universe set that limit at the moment of its creation, and it has held across every scale we've ever been able to test. So, 1 light year is the distance you'd cover if you could travel at the absolute maximum speed the universe permits, sustained for an entire year without stopping. That's the scale of what we're dealing with before we've even climbed aboard. Here's what 1 light year actually represents in terms of our own solar system's scale. Most people picture the solar system as ending just beyond Neptune. Neptune orbits at about 30 astronomical units from the Sun. But the solar system doesn't end there. Not even close. Beyond Neptune lies the Kuiper Belt, a ring of icy objects extending from about 30 to 50 astronomical units. Pluto is a Kuiper Belt object. So are Eris, Makemake, Haumea, and thousands of smaller bodies. The Kuiper Belt gives way to the scattered disk, a sparse region extending to several hundred astronomical units. And then, much further out, the Oort cloud. The Oort cloud is a vast, roughly spherical shell of icy bodies surrounding the entire solar system. Its inner edge is estimated to begin somewhere around 2,000 astronomical units from the Sun. Its outer edge extends to perhaps 100,000 astronomical units, possibly further. This is the region that long-period comets come from bodies with orbital periods of hundreds or thousands or millions of years. Perturbed by gravitational encounters with passing stars and sent tumbling inward toward the Sun on elongated orbits. When we watch a spectacular comet arc across the inner solar system, it has typically fallen from the Oort cloud, a journey that took it from perhaps 50,000 astronomical units down to within a few astronomical units of the Sun. 1 light year in astronomical units is 63,241 astronomical units. This puts the outer edge of the Oort cloud at roughly 1 light year from the Sun. The solar system doesn't end at Neptune. It doesn't end at Pluto. Its gravitational influence and the population of bodies bound to it extends to approximately 1 light year. The first light year of any interstellar journey is, in a real physical sense, the crossing of our own solar system's outermost territory. You wouldn't cross it and arrive somewhere new. You'd cross it and arrive at the boundary between our Sun's domain and the true void. At the outer edge of the Oort cloud, looking back, the sun is still the brightest object in the sky. Still clearly identifiable. Still gravitationally dominant over everything around you. But distant. 63,000 times further than Earth is from the sun. A point of light, not a disk. And looking forward in any direction that isn't toward our own star, the nearest stellar systems are still more than 3 light-years away. The void between us and them is neither our home system nor their home system. It belongs to no star. It exists because stars are rare and space is vast, and the universe was built at those proportions. Now, take a breath. Because the question isn't just how far 1 light-year is. The question is, what actually happens to you if you try to cross it? What happens to time? What happens to your body? What the ship around you is experiencing at every moment? What the universe looks like from inside something moving fast enough to matter? The answers are strange. Some of them are genuinely disturbing. And none of them are intuitive, because nothing in everyday life prepares you for velocity at a meaningful fraction of the speed of light. Your brain evolved on a planet where the fastest things moved at a few miles per hour, and the physics relevant to survival was entirely Newtonian. The universe beyond that is genuinely alien, and traveling 1 light-year is an encounter with that alien physics on every level simultaneously. The first thing to establish is speed. If you're going to travel 1 light-year, you need to pick a velocity and commit to it. Your choice of speed changes everything. The duration of the journey, the physical dangers, the warping of time, the energy requirements, the radiation exposure. The forces on the hull, everything scales with how fast you're going. Start with something we actually understand. The fastest spacecraft humanity has ever built is the Parker Solar Probe. At its peak, during close approach to the Sun, it reaches roughly 430,000 miles per hour. That is genuinely extraordinary by any human standard. At that speed, you could cross the continental United States in under 2 seconds. You could circle Earth in about 55 seconds. It is the fastest object humans have ever launched, and it is nowhere near fast enough. At 430,000 miles per hour, crossing 1 light-year takes over 15,000 years. The entire span of recorded human civilization fits inside that travel time, and still leaves more than 10,000 years remaining. 15,000 years at our fastest speed to cover 1 light-year. The gap between what we can currently achieve and what the universe requires is not a gap. It is an abyss. To cross 1 light-year in any time frame, a single human could survive. You would need to travel at a substantial fraction of the speed of light. At 10% of light speed, about 67 million miles per hour, the journey takes 10 years as measured from Earth. At 20% of light speed, 5 years. At 50% of light speed, 2 years. At 90%, about 13 months. At 99% of light speed, just over 12 months. These are the velocities where the physics starts getting genuinely strange. And strange is putting it mildly. The acceleration phase is where the physics first makes its demands clear. From the moment of departure, every second of thrust costs energy at a rate the vehicle's systems must sustain continuously. You can't simply go from 0 to 10% of light speed in a matter of hours. The forces involved at high acceleration would destroy both the ship's structure and the people inside it. A sustained acceleration of 1g, identical to the pull of gravity on Earth's surface, would be physiologically ideal for the crew. It would simulate normal gravity throughout the acceleration phase without requiring a rotating habitat. The cardiovascular system stays conditioned because it's still working against effective gravitational pull. The bones stay loaded because the crew is effectively standing in 1g. The vestibular system works normally because there's a consistent sense of up and down. From a crew health standpoint, 1g constant acceleration is the best possible scenario. And at 1g, the time to reach meaningful fractions of light speed is calculable. Reaching 10% of light speed from rest at 1g takes about 35.5 days. Reaching 50% of light speed takes about 201 days. Reaching 90% of light speed takes about 730 days. These are manageable timescales. The problem is not the duration of the acceleration. The problem is the energy it requires. For a hypothetical crewed ship of 1,000 metric tons, which is conservative for something that must carry everything its crew needs for years, sustained 1g acceleration for a year requires energy on the order of many times the total current annual energy production of Earth. That's the entire planet's electricity generation for a year, for one ship. One acceleration phase. This is not a cost that scales gradually better as technology improves. The physics does not offer a discount. The Lorentz factor requires a specific amount of energy to reach a specific velocity for a given mass. What changes with technology is efficiency, how well you convert stored energy to thrust, how much waste heat you generate, how completely you can extract energy from your fuel. Better engineering can approach the theoretical limit. It cannot exceed it. The strangeness begins with something Albert Einstein discovered in 1905. When he published The Special Theory of Relativity, among its results was one that nobody expected and that took decades to become fully accepted. Speed affects time, not metaphorically, not as a philosophical statement about the subjectivity of experience. Physically, measurably, the faster you move through space, the slower time passes for you compared to everything you left behind. This is called time dilation, and it is one of the most verified predictions in all of physics. GPS satellites orbiting Earth at about 8,000 miles per hour experience it. Without corrections for relativistic time dilation, GPS systems would accumulate position errors of several miles per day. The system would become useless within hours of operation. The correction is built into every satellite in the constellation because the effect is real and the equations are precise. Without that correction, your navigation app would be wrong by several miles by early afternoon. Particle accelerators demonstrate time dilation every single day. Muons are unstable subatomic particles with a half-life of about 2.2 microseconds. They're created in the upper atmosphere when cosmic rays strike air molecules at altitudes of about 9 miles. At the velocities, muons travel very close to light speed. They should decay long before reaching the ground, given how short their half-life is and how far they have to travel. Simple multiplication says they should be gone before they get anywhere near sea level. They aren't. On Earth's surface, they're still present in numbers that only make sense if time has slowed for them during the journey down. It has. The Lorentz factor predicts exactly how many survive the trip. The prediction matches observation every single time experimenters have checked. This is not interpretation. This is a number and a measurement that agree to the precision of the instruments used. And if you're traveling 1 light year at relativistic speed, time dilation is not a footnote in the physics. It is the defining fact of your existence aboard that ship. Einstein's insight in 1905 came from asking a question that sounds simple, but had never been answered properly. What does it mean for 2 events to happen at the same time? If you're standing still and 2 lightning bolts strike the ground a few hundred feet apart, and both strike simultaneously from your perspective, does someone moving relative to you agree that they were simultaneous? Newton's physics assumed yes. Of course, they're simultaneous. Time is time, the same for everyone. Einstein showed the answer is actually no. 2 events that are simultaneous for a stationary observer are not simultaneous for an observer moving relative to them. The simultaneity of events is not absolute. It depends on the observer's state of motion. This isn't a philosophical statement about perception. It's a physical statement about the nature of time. Time is not a single universal river running the same rate everywhere. It is a local property of the observer. Each object, each person, each clock carries its own version of time, and those versions run at rates determined by how fast that object is moving and how deep it sits in a gravitational field. The consequence for travel is that 2 clocks, synchronized at the same location and then separated, one staying put, one moving at high velocity, will no longer agree when they're reunited. The moving clock will have logged fewer seconds. This has been confirmed with atomic clocks on aircraft. The clocks flown around the world tick slightly slower than the ones left on the ground. The difference is tiny nanoseconds. But it is real, it is measurable, and it matches the prediction of special relativity exactly. Scale that experiment to a ship crossing 1 light year at 99% of light speed, and the difference is not nanoseconds. It is weeks. The physics is the same, only the scale is different. Here is how the numbers actually work. There's a quantity physicists call the Lorentz factor. It describes how much time slows for a moving object relative to a stationary observer. At everyday speeds, a car on a highway, a commercial jet, even a rocket to the space station, the factor is so close to 1 that the time difference is a few nanoseconds over a lifetime of movement. Completely immeasurable, without atomic clocks. Irrelevant to your daily existence in every practical sense. But as you approach the speed of light, the factor climbs. At 10% of light speed, it's barely above 1.005. Time passes about 0.5% slower for you than for stationary observers. Real, but small. At 50% of light speed, it's about 1.15. For every year you experience, 1.15 years pass on Earth. Not dramatic yet, but growing. At 90% of light speed, the factor reaches approximately 2.3. For every year you age aboard the ship, 2.3 years pass outside it. At 99% of light speed, it jumps to about 7.1. For every 7 years that pass on Earth, you personally live through one. At 99.9% of light speed, the factor reaches approximately 22. For every year you experience on board, 22 years pass everywhere else. This has a concrete consequence for a 1 light-year journey. A ship traveling at 99% of light speed takes about 1 year and 13 days to cross 1 light year. Measured from Earth, that's what an external observer on Earth would measure. But for the crew inside the ship, with the factor at 7.1, they age only about 7 weeks. They launch. They cross 5.88 trillion miles of empty interstellar space. They arrive at their destination, and they have personally experienced about 52 days. Meanwhile, back on Earth, over a year has passed. Families are older. Events have occurred. The world has moved forward at a rate completely independent of what was happening aboard that ship. This isn't approximation. This isn't a philosophical thought experiment about subjective time. It is what the equations predict, what every experimental test at every accessible scale confirms, and what would actually happen. The universe keeps separate clocks for things moving at different speeds. Velocity is the dial that controls how far those clocks diverge. And the divergence, once it has occurred, is real and cannot be reversed. You cannot go back and resynchronize. You've lived different amounts of time. That's the situation. The precision of the Lorentz factor deserves a closer look. Not because it's an impressive number, but because of what that precision implies. The factor isn't approximate. It isn't a rough guide. It is an exact mathematical relationship that has been verified at every velocity and energy scale, accessible to experiment. When a muon survives its journey through the atmosphere longer than its half-life should allow, the Lorentz factor predicts exactly how much longer it survives. Not approximately. Exactly. When atomic clocks are flown on aircraft and compared to clocks left on the ground, the time difference is exactly what the Lorentz factor predicts. When particle accelerators measure the behavior of particles moving at 99.999% of light speed, the particles behave exactly as the Lorentz factor says they should. The agreement between theory and measurement across 9 decades of experimental physics is not suggestive. It is definitive. The physics is not a model that might be superseded. Special relativity is as tested and confirmed as any scientific theory we have. The only scientific framework more thoroughly tested is quantum mechanics, and the two frameworks agree with each other in every domain where both apply. This matters for the journey we're describing, because it means we're not extrapolating from a theory that might be wrong. We're applying a confirmed physical law to a new set of conditions. The numbers for a 1 light-year voyage, the 52 days of crew, aging at 99% of light speed, the year plus of Earth time, are not predictions that might turn out differently when tested. They are the results of applying verified physics to the specific parameters of the voyage. The universe has already told us how time behaves at those velocities. We know the answer. We just haven't made the journey yet. Now, step inside the ship and consider what the journey actually looks like from there, because it is nothing like flying through space in any film you've ever watched. The visual experience of high-velocity interstellar travel is deeply alien in ways that are completely described by known physics. We don't need to speculate about what you'd see. We can calculate it. The first visual effect is the Doppler shift. You've encountered this with sound. A vehicle approaching you has its engine noise compressed to a higher pitch. As it passes and recedes, the pitch drops. The sound waves are compressed ahead of the vehicle's motion and stretched behind it. Light behaves the same way, because light is also a wave. When you're moving toward a light source at a significant fraction of the speed of light, the wavelengths of that light are compressed. The light shifts toward shorter wavelengths, toward blue, toward violet, and at extreme velocities, toward ultraviolet and beyond. When you're moving away from a source, its wavelengths stretch toward red and then into infrared. At 10% of light speed, the effect is noticeable but subtle. Stars in the forward direction appear slightly bluer than normal. Stars behind you appear slightly redder. The sky still looks broadly familiar. At 50% of light speed, the shift is pronounced. Stars ahead that were yellow now look blue-white. Stars that were orange-red now look yellowish. The forward hemisphere of the sky has a notably different palette than the one you knew. At 90% of light speed, the Doppler shift is extreme. Visible light from stars directly ahead has been compressed into ultraviolet frequencies, wavelengths your eyes cannot detect. Stars that were luminous and visible have effectively gone dark from your perspective. Their light shifted entirely out of your visual range. What replaces them in the visible spectrum is infrared light from cool, dim stars that were near invisible from Earth, now shifted up into wavelengths. Your eyes can register by your velocity. The forward sky is populated by different stars than the ones you knew from Earth. Stars that were invisible before. A different arrangement. A different sky. And at 99% of light speed, most of what you'd see ahead has been shifted so far into ultraviolet, and beyond that, the forward arc looks peculiar, even in terms of what light is present at all. The second visual effect is called relativistic aberration. At rest, stars are distributed across the entire sphere of the sky in roughly the pattern your star charts show. When you start moving at relativistic velocity, the geometry of incoming light changes. Stars that were off to the side appear to shift toward the direction of travel. Stars that were behind you crowd forward. The faster you go, the more extreme the crowding. At 50% of light speed, the entire night sky appears compressed toward the forward hemisphere. The rear half of the sky looks noticeably emptier than normal. At 90% of light speed, almost the entire visible stellar content of the universe has been swept into a cone spanning about 26 degrees ahead of you. Stars that should be to your left, to your right, behind you, all compressed forward by your motion. The sky in the aft direction has gone nearly black. At 99% of light speed, that cone has narrowed further. Virtually all visible starlight crowds into a tight ring surrounding a point directly ahead. Behind you, almost complete darkness. Not because there's nothing there, but because the light from everything in those directions has been bent forward by your velocity. The physics of wave propagation and motion don't care that you'd prefer the stars to stay where you expect them. They move. And it's not just starlight. The cosmic microwave background, the faint afterglow of the universe's beginning, normally spread uniformly across the entire sky at a temperature of about -455 degrees Fahrenheit. Also, blue shifts forward with your velocity. Normally, this radiation is completely invisible to human eyes. It exists in microwave frequencies, far below what you can see. But at 99% of light speed, it has been compressed into visible and ultraviolet wavelengths. The forward arc glows with it light from no particular star, but from the universe's oldest light, the relic radiation of the Big Bang itself, made visible by the speed you're traveling. Standing at the forward viewport of a ship, crossing 1 light year at near light speed, what you'd see would be unlike anything any human has ever witnessed. A blazing ring of compressed light ahead. Darkness almost everywhere else. Stars you've never seen before, because they were previously in the infrared. Stars you expected to see, gone dark, because their light has been pushed beyond your visual range. The universe rearranged by your velocity into something completely new. Now we have to talk about something that almost everyone overlooks when imagining interstellar travel. The interstellar medium. Space is not empty. This is one of the most important physical facts about interstellar travel, and one of the most commonly misrepresented. Between the stars, there is gas and dust. The interstellar medium. A thin distribution that fills the galaxy. On average, roughly 1 atom per cubic centimeter in typical interstellar regions. Mostly hydrogen, the simplest and most abundant element in the universe. About 10% helium by number. Traces of carbon, oxygen, nitrogen, iron, and other heavier elements, scattered remnants of stars that lived and exploded before our solar system formed. And scattered throughout, microscopic dust grains, particles of silicate minerals and carbon compounds, typically ranging from nanometers to micrometers in size. By any laboratory standard, this is an extreme vacuum. The best vacuum chambers on Earth contain several 100 million atoms per cubic centimeter. Interstellar space has one. To put that in perspective, the best vacuum we can achieve in a laboratory is still roughly 100 million times denser than typical interstellar space. Interstellar space is not just empty. It is almost incomprehensibly empty. At low speeds, this thinness is entirely irrelevant to a spacecraft. Voyager 1 has been traveling through interstellar space since it crossed the heliopause in 2012. It has been out there for over a decade. Its instruments still function. 1 hydrogen atom per cubic centimeter presents no practical problem at 38,000 miles per hour. The atoms hit the hull so rarely and with so little energy that the cumulative effect over decades of travel is negligible. That changes completely at relativistic velocity. At 10% of light speed, the kinetic energy of a single hydrogen atom striking the bow of your ship, measured in the ship's reference frame, is approximately 400 million electron volts. This is the energy range of high-energy cosmic ray particles. The same particles that space agencies worry about when planning long-duration missions. At typical interstellar densities, the bow encounters on the order of several hundred atoms per second per square meter of frontal area. Each collision, individually, deposits a small amount of energy. But collectively, over months and years of travel, those collisions accumulate. They heat the hull material. They create radiation damage in the molecular bonds of whatever the hull is made of. They produce secondary particles, fragments from disrupted atomic nuclei that propagate deeper into the material. Over a 10-year voyage at 10% of light speed, the cumulative fluence of hydrogen atoms hitting the forward shield would be enormous. the material damage would be real and would require the shield to be designed specifically to handle it. At 90% of light speed, the situation becomes severe rather than manageable. Each hydrogen atom the ship encounters now carries, relative to the ship, about 1,200 million electron volts of kinetic energy. That is the energy range of protons produced by large research synchrotrons, particle accelerators, that were pushing the frontier of physics in the mid-20th century. At 99% of light speed, the energy rises further still, into ranges that approach the most powerful accelerators ever built. A ship at 90% of light speed is flying nose first into a continuous, low-flux version of that particle beam. The interstellar hydrogen atoms, from the ship's reference frame, are accelerated to near light speed. The hull doesn't know whether it's a fast proton hitting a stationary wall or a stationary wall hitting a fast proton. These are physically identical situations, and the damage at those energies is not negligible. High-energy protons striking metal can shatter atomic nuclei, producing cascades of secondary particles, neutrons, pions, heavier nuclear fragments, gamma rays that propagate outward through the shielding material. If secondary particles reach the crew compartment, they deposit energy in biological tissue. The shielding required to protect crew members from the interstellar medium at 90% of light speed would need to be substantial. Meters of dense material at the leading edge of the ship. Water is among the better practical choices. Hydrogen nuclei absorb high-energy particle energy more efficiently without generating as many damaging secondary particles as metals like aluminum or iron do. The issue with water is mass. Meters of water is a very large amount of mass, and mass, at relativistic velocity, is the central problem that everything in interstellar travel design returns to eventually. The energy required to move mass to relativistic speeds is one of the most important physical facts about interstellar travel, and one of the most consistently underestimated. The relationship is not linear. At everyday velocities, kinetic energy scales roughly as 1/2 times mass times velocity squared. Large for large velocities, but growing in a way that's at least intuitively graspable. As you approach the speed of light, the relationship changes fundamentally. The energy required to gain additional velocity grows according to the same factor that dilates time, the Lorentz factor. This factor accelerates toward infinity as velocity approaches the speed of light. At 50% of light speed, you need to supply energy equivalent to about 15% of the ship's rest mass energy to get it moving at that speed. At 90% of light speed, you need about 130% of the rest mass energy. Rest mass energy is the energy equivalent of the ship's mass. From Einstein's equation, E equals mc squared. E equals mc squared says that mass and energy are interchangeable. The energy equivalent of 1 kilogram of mass is approximately 90 petajoules. That's roughly 21 megatons of explosive equivalent. To accelerate 1 kilogram of anything to 90% of light speed requires supplying energy equal to about 117 petajoules. For a ship large enough to carry a crew with life support, radiation shielding, food, water, medical supplies, navigation systems, communication equipment, spare parts, the total mass would be at minimum several thousand kilograms, likely much more. Each kilogram costs roughly 117 petajoules to accelerate to 90% of light speed. And then you need to decelerate at the destination. Same cost again. The most energetically dense fuel conceivable is antimatter. When a particle of matter meets its corresponding antiparticle, they annihilate completely and totally. 100% of their combined mass converts to energy, exactly as E equals mc squared describes. 1 kilogram of antimatter annihilating, with 1 kilogram of ordinary matter releases about 180 petajoules. Nothing in all of physics can match this energy density. It is the theoretical ceiling, the absolute maximum energy available from any given mass of fuel. And even with perfect antimatter fuel, the mass ratios for a crude interstellar ship at high relativistic velocity are punishing. The Tsiolkovsky rocket equation, first published in 1903 by Russian mathematician Konstantin Tsiolkovsky, and as unforgiving now as it was then, describes the fundamental relationship between propellant mass and the velocity change it produces. For relativistic velocities, the relationship compounds. To accelerate a ship carrying even 1,000 kilograms of useful payload to 90% of light speed and then stop it again at the destination, you need far more than 2,000 kilograms of antimatter, because you have to accelerate the fuel too. And the fuel for the fuel. The rocket equation compounds the way compound interest compounds, except much faster and in the wrong direction for your mass fraction. The result is that the vast majority of the ship's mass at launch would need to be fuel. A small fraction would be the actual payload, the people, and the equipment they need to survive. And we cannot produce antimatter in any quantity approaching what this would require. The combined output of all particle accelerators on Earth generates nanograms of antimatter per year. A nanogram is 1/1000th of a gram. An interstellar mission using antimatter fuel would require kilograms, possibly tons. The production gap between what we can make and what we would need is roughly 10 orders of magnitude. That is not a gap engineering can bridge with incremental improvements. That requires physics we don't currently have, at scales we can't currently achieve. The universe does not provide shortcuts. Either the energy exists or the journey doesn't happen. Consider what Project Orion tells us about this gap. In the late 1950s and early 1960s, the United States government funded serious engineering work on a propulsion concept that sounds extreme until you realize it was based entirely on existing technology. The idea was to propel a spacecraft by detonating nuclear bombs directly behind it. A massive shock absorber plate at the aft end of the ship would capture the impulse from each explosion. Several explosions per second would accelerate the vehicle. The bombs existed. The shock absorber engineering was worked out. Freeman Dyson, one of the most formidable physicists of the 20th century, calculated trajectories and performance in detail. Project Orion was not fringe science. It was a serious engineering effort conducted by serious physicists and engineers using real hardware and real calculations. Large Orion vehicles could theoretically reach several percent of light speed, not a meaningful fraction of what interstellar travel requires, but a real, substantial improvement over anything built before or since. The project was ended by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Not by physics, not because the concept didn't work, by policy. Orion is a data point. It shows that the gap between what we can build today and what interstellar travel requires is not absolute. Every serious interstellar propulsion concept that has been rigorously evaluated, Orion, Project Daedalus, laser sails, magnetic sails, identifies real physics that could in principle provide meaningful performance. None of them are ready. None of them approach the full requirements. But they are all pointing in the same direction, toward the physics that works, away from what doesn't. Think carefully about deceleration, because it's the half of the problem that most discussions shortchange, and the physics is unforgiving about it. Assume you've solved propulsion. You've found the energy, built the engines, accelerated your ship to 90% of light speed. You're crossing 1 light year. You're going to arrive somewhere, and you need to stop. There is no brake that works in deep interstellar space. No air resistance. No runway. No medium to push against in any useful sense. The interstellar medium creates drag so small it's a navigational correction over years, not a meaningful deceleration force. The only way to slow from 90% of light speed is to fire your engines in the direction of travel. Thrust yourself backward against your motion and sustain that thrust until velocity drops to something manageable. This consumes the same amount of energy as the acceleration phase. If you carry fuel for both legs, the initial launch mass grows substantially. The fuel for deceleration has to be accelerated during the outbound trip, which requires more fuel to accelerate the deceleration fuel. The rocket equation compounds again. One-way missions have simpler energy budgets than return trips, which is part of why serious proposals for early interstellar missions involve one-way voyages. You only pay the acceleration cost once. But one-way means no return. The first humans to leave the solar system permanently, knowing they won't come back, accepting that as the price of going. The physics is more tractable. Everything else about it is harder. For missions that intend to stop at a destination and return, the energy cost is at least 3 to 4 times the one-way acceleration cost, accounting for deceleration and the return trip. The compounding makes already enormous numbers more enormous still. Proposals to sidestep. This include laser propulsion. A massive laser array in the home system pushes the ship outbound without the ship carrying propellant for that leg. This makes the ship lighter, and the energy cost comes from the laser installation, not from fuel aboard. But deceleration still must happen at the destination. Without a laser array at the other end, the ship carries its own propellant to stop, which adds mass, which the laser has to accelerate. The problem shifts, but doesn't disappear. Stellar light sails for braking at the destination have been proposed. For a ship of practical mass, the required sail size becomes enormous. And arriving at exactly the right trajectory and distance from the destination star to use its light for braking after years of travel requires extraordinary navigational precision. Every proposal has constraints. Every constraint has consequences. Physics charges a fee for crossing interstellar distances, and the fee is not negotiable. In 1978, the British Interplanetary Society published the Daedalus study, a 2-year engineering feasibility study for an unmanned interstellar probe. The target was Barnard's star, about 6 light-years away. The proposed vehicle would use inertial confinement fusion, small pellets of deuterium and helium, 3 compressed to fusion by electron beams, triggered 50 times per second. The vehicle would reach 12% of light speed. The one-way trip to Barnard's star would take about 50 years. The mass budget, around 54,000 metric tons at launch. The engineering challenges were enormous. The helium. 3 requirements alone, fuel for the first stage, would require mining the atmosphere of Jupiter. Not because the designers were being unrealistic, because the physics requires it. That's how much fuel a fusion drive needs to push 54,000 metric tons to 12% of light speed. The Daedalus study is notable, not because it solved the problem, but because it characterized it. It showed, with rigorous engineering calculation rather than vague speculation, what the requirements actually are. The Icarus Interstellar project, started in 2009, continued that work. The Breakthrough Starshot Initiative, funded in 2016, targeted a different approach. Entirely tiny light sails, propelled by a ground-based laser array, to 20% of light speed, in recognition that the mass problem is the central problem. Make the spacecraft small enough, and the energy requirements drop from impossible to merely extremely difficult. Each of these is a different engagement with the same physical constraints. Different proposals, same constraints. The constraints don't change. What changes is how seriously people try to work within them. Set the energy problem aside. Assume it's solved. The ship is moving. You're crossing 1 light-year at a substantial fraction of light speed. Now, the human body has its own separate and serious objections. The human body evolved over millions of years to function in one specific set of conditions. One gravitational field, roughly 9.8 meters per second squared, the pull of a rocky planet with Earth's mass. 1 atmospheric pressure, about 101,000 pascals at sea level. 1 radiation shielding environment provided by Earth's magnetic field and several dozen miles of atmosphere above your head. Every system in your body, skeletal, muscular, cardiovascular, neurological, immunological, hormonal, sensory, was shaped by millions of years of evolution in those conditions. Remove them, and the systems adapt. But biological adaptation doesn't mean improvement. It means optimization for the new environment. And the new environment is not the one your biology was built for. Start with gravity. In a ship coasting at constant velocity through interstellar space, there is no effective gravity. Everything floats. This feels unusual for a few minutes and pleasant for a few hours. Over days and weeks, it begins to become a systematic dismantling of your body. Bone is not dead, structural material like steel or concrete. It is living tissue in constant dynamic remodeling. Specialized cells, called osteoblasts, build new bone by depositing calcium phosphate mineral into a protein matrix. Other cells, called osteoclasts, break bone down, dissolving the mineral back into the bloodstream. On Earth, mechanical stress from standing and walking provides the signal that tells osteoblasts to maintain their pace, to keep building bone at the rate it's being broken down. Without that signal, the balance tips. Osteoclasts continue their work at the normal rate. Osteoblast activity slows. Bone density falls. The rate is roughly 1 to 2% of mineral density per month in the most affected regions. The weight-bearing bones of the spine, the hips, the upper leg. Astronauts on 6-month International Space Station missions lose an average of 10 to 15% of their bone mineral density. Their skeletal systems are measurably weaker after half a year. Not metaphorically weaker. Measurably, quantifiably weaker in ways that show up on bone density scans. Recovery after returning to Earth takes many months of weight-bearing exercise and physical therapy. Some density loss never fully recovers. The skeleton has adapted to a new baseline, and the old baseline is only partially retrievable. Now, extend that 6 months to the years that a 1 light-year journey at 10 or 20% of light speed would require. 10 years at 10% of light speed. The people who would have to find out are the ones inside the ship. Years from anyone who could help, in a medical situation that has no established treatment protocol. We might be wrong about the extrapolation. The biology might plateau, but we don't know. And that uncertainty, at the distances and timescales of interstellar travel, is a serious problem. Muscle follows identical logic. On Earth, simply being upright requires continuous low-level muscular work. Your postural muscles, the deep muscles of the back, the core, the legs, fire constantly to keep you from collapsing. Walking, sitting, standing, shifting weight, all of these engage muscle chains that maintain strength and mass. In microgravity, that demand disappears. The muscles that evolved to work against gravity have no load to work against. They atrophy rapidly. International Space Station, astronauts follow mandatory daily exercise protocols, 2.5 hours of structured resistance training, and cardiovascular exercise every single day. Not optional. Not recommended. Required by mission rules. And despite that mandatory 2.5 hours, they still lose up to 20% of muscle mass over a 6-month mission. The exercise slows atrophy. It cannot stop it. The body continuously optimizes toward the actual environment it's in, and the actual environment is one where muscles don't need to be as large or as strong. Over years, the accumulated adaptation deepens. Muscles that remain restructure toward endurance performance in zero gravity rather than toward the load-bearing, high-force output needed in a gravitational environment. Returning to gravity after years of this is not simply a matter of doing physical therapy for a few weeks. It would require rebuilding from a state that has no established rehabilitation protocol. The cardiovascular system adapts to microgravity in ways that are equally problematic and perhaps more insidious. On Earth, the heart pumps blood upward against gravity to reach the brain. This is not a trivial task. The brain sits about 18 to 20 inches above the heart. Getting blood there requires the heart to generate enough pressure to overcome gravity across that distance. In microgravity, there is no upward. Blood doesn't pool in the legs as it normally does. Fluid redistributes toward the head and chest, a condition astronauts often describe as feeling like they have a permanent head cold, with puffy faces and nasal congestion. The body, sensing elevated pressure in the upper body, interprets this as excess fluid and begins excreting it. Blood volume decreases. The heart, no longer fighting gravity to reach the brain, doesn't need to work as hard. It adapts over weeks and months, becoming somewhat smaller, remodeling toward a less stressful workload. This adaptation is appropriate for the environment the heart is actually in. but it's the wrong adaptation for a return to gravity. Astronauts returning from 6-month missions frequently need assistance leaving the spacecraft. Their cardiovascular systems have deconditioned to the point where suddenly having to pump blood upward against gravity again is a shock. Standing causes blood pressure to drop. The brain doesn't get adequate perfusion. People faint. Reconditioning takes weeks of gradual re-exposure. After years of microgravity, the deconditioning would be far more profound. The longest continuous spaceflight on record is 437 days by Russian cosmonaut Valery Polyakov aboard the Mir space station. An interstellar voyage at 10% of light speed takes a decade. That's more than 8 times longer than the longest anyone has ever been in microgravity. Whatever happens to cardiovascular health over that timescale, we're extrapolating into unknown territory. Vision changes in ways that weren't fully appreciated when space medicine was in its early decades. About 60% of astronauts who spend extended time aboard the International Space Station report visual changes after their missions. Many of these changes are subtle. Some are significant. A few are permanent. The leading explanation involves intracranial pressure, the pressure of fluid surrounding the brain and optic nerves. Without gravity pulling fluid toward the feet, the normal downward distribution of cerebrospinal fluid changes. More fluid accumulates around the brain and optic nerves than would normally be there in a person standing upright. The elevated pressure can cause swelling of the optic disc, the point where the optic nerve meets the retina inside the eye. It can also subtly deform the eyeball itself, changing its focal length. The most common result is a shift toward farsightedness. Some of this reverses after returning to Earth. Some doesn't. There are astronauts with permanently reduced visual acuity following 6-month space missions. Over years of elevated intracranial pressure, the accumulated damage would be greater. And compromised vision on an interstellar ship is not a minor inconvenience. Identifying problems in systems requires seeing them. Reading instrument displays requires seeing them. Performing delicate repairs in confined spaces requires seeing what you're working on. The crew's ability to keep the ship functioning and to keep themselves alive depends on them being able to see what they're doing. The immune system changes in microgravity as well, and the changes are not in a useful direction. Studies have shown that immune cells exhibit reduced functional capacity in microgravity. Their proliferation is impaired. Their ability to recognize and respond to pathogens is diminished. Several viruses that healthy immune systems normally keep suppressed show signs of reactivation in astronauts on longer missions. Epstein-Barr virus, which causes mononucleosis and is present in the majority of adults in a dormant state. The varicella-zoster virus, which causes chickenpox initially and then remains dormant, capable of reactivating as shingles. Cytomegalovirus, another herpes family virus that stays latent in most infected people. In astronauts, these viruses become detectable at elevated levels in saliva and other body fluids during missions. The immune system is suppressing them less effectively. Over a multi-year voyage, in a small crew living in a closed and self-contained habitat, this immune suppression compounds over time. Any illness that develops encounters immune systems running below their design capacity. Any pathogen from the crew's own dormant viral reservoirs that reactivates encounters less effective resistance. and medical care is whatever was brought on the ship. There is no hospital. There is no physician outside the crew, no specialist to evacuate to. Every medical event is managed with the training and supplies aboard. With communication delays of months to years for any advice from Earth, the medical challenge of an interstellar voyage is not just that space is hostile, it's that you face the consequences of that hostility with very limited resources and no possibility of external help. The psychological dimension of an interstellar voyage is a challenge that parallels the biological ones, and it is no less severe. Human beings evolved in social environments. Our ancestors lived in groups. Survival depended on community, on the exchange of resources, information, and support that only groups provide. Our psychology is calibrated for a world with other people in it. Remove that environment, and human psychology responds. Not catastrophically in every case, but measurably, reliably. The research on isolated and confined environments, Antarctic winter overstations, submarine crews on long patrols, space station crews gives a consistent picture of psychological shifts over time. Mood destabilizes over extended isolation, interpersonal conflicts, which in normal social environments are diffused by the presence of many people and the ability to seek different company, concentrate and intensify in small groups with no exit. Cognitive functions associated with emotional regulation can become less effective over months of confinement. Performance on tasks requiring sustained attention degrades in ways that are statistically significant. Sleep quality tends to deteriorate in isolated and confined environments, particularly when natural light cycles are absent or disrupted. And the particular character of interstellar isolation adds dimensions that Antarctic or submarine isolation doesn't have. Communication with home degrades continuously. It's not simply that contact is limited from the start. The connection actively worsens. Every month, the signal delay grows. Every month, what arrives from Earth is older. The crew watches. In real time and in slow motion, the communication link to everything they knew attenuate toward uselessness. 6 months into the voyage, Earth's responses arrive weeks after the questions were sent. A year in, it's months. At 5 years in, the delay is half a year each way. Nothing happening on Earth now can be known aboard the ship for 6 months. The world they left continues without them, in ways they can only learn about with enormous delay. People they care about experience things, good things, and difficult things, and the crew learns about those events long after the fact. Every exchange is a conversation with the past. Consider, specifically, what communication at 1 light year means for a crew member trying to maintain any relationship with people back on Earth. You send a message. You describe what happened today, what you're thinking, how you're doing. That message travels at light speed, the fastest anything can move, and arrives at Earth a year later. The person you care about reads a description of who you were and what you experienced a year ago. They write back immediately, the same day they read your message. They describe their life, their thoughts, their current situation. Their response travels back to you at light speed. It arrives a year after they sent it. 2 years after you sent your original message, you receive a response to it. You're reading about what their life was like a year ago, written in response to what your life was like a year before that. The exchange is real. The care is real. The words are genuine, but you are both responding to each other's past selves. The conversation is always conducted in a gap. Any statement you make is about a situation that has been resolved, changed, or evolved long before the response arrives. Any response you receive addresses a you that no longer exists in quite the same form. The emotional weight of this accumulates. Not immediately. Not in the first months, when the delay is still weeks rather than years. But over the full span of the voyage, the correspondence becomes something different from communication. It becomes a form of historical correspondence. Like writing letters to someone who lived in the past and receiving their replies about your future, except it is real. It is happening in the present tense to both parties. It is just that the present tense for each of you no longer overlaps. The psychological weight of that, sustained over years, is a genuine challenge that current research on isolated environments can identify but not fully characterize. Because the delay itself is a new variable. Antarctic stations are isolated, but they can call Earth in near real time. Submarine crews are cut off during a patrol, but the patrol ends. The crew of an interstellar ship faces isolation, whose defining feature is not just its duration, but its deepening. Every day, the link is a little more attenuated. Every month, a little more of a historical record than a conversation. Over years, the gap becomes the dominant fact of their relationship to Earth. And the only people who know what it actually feels like are aboard the ship. The most reliable solution to most of the microgravity problems is artificial gravity through rotation. This is not exotic technology. It's basic physics. A rotating structure creates centripetal acceleration that is physically indistinguishable from gravity to anyone standing on the inner rim. Your cardiovascular system, your skeletal system, your vestibular system, your immune system, all respond as they would to gravity. The bones get the mechanical loading they need. The heart gets the gravitational challenge it evolved to handle. The fluid distribution in the body returns to normal. The engineering challenge is making it work at the right scale and rotation rate. The human vestibular system can tolerate rotation up to about 2 rotations per minute without producing significant disorientation. Above that rate, the Coriolis effect becomes noticeable. When you move your head in a rotating environment, objects appear to curve unexpectedly. This causes nausea and disorientation in most people. 2 rotations per minute is roughly the comfortable upper limit. To produce 1 G of effective gravity at 2 rotations per minute, a rotating ring needs a radius of about 738 feet. That's approximately the length of 2 football fields, end to end. This is not physically impossible. Multiple credible engineering studies over several decades have proposed rotating habitats at this scale. The designs are complex, but not based on unknown physics. But it adds mass. Every structural element of that rotating ring is mass that the propulsion system must accelerate to the ship's cruise velocity. And mass, as we've already established, is the thing the energy problem is most sensitive to. The solution to the biology problem imposes additional costs on the energy problem. These 2 challenges are not independent. Solving one makes the other harder. This is the pattern that runs through all of interstellar engineering. The problems interconnect. Every solution has costs. Every cost has consequences. The universe enforces this consistency. One thing the energy calculations make relentlessly clear is the extraordinary sensitivity to mass. Every kilogram of mass aboard the ship is a kilogram that the propulsion system must accelerate to the cruise velocity and then decelerate at the destination. The energy cost per kilogram is fixed by the velocity and the Lorentz factor. It cannot be reduced by clever engineering. The only variable that engineering can meaningfully touch is how much mass is aboard. This creates a systematic pressure on every design decision. Structural materials are chosen for the highest possible strength-to-mass ratio. Life support systems are designed to be as compact and light as possible while maintaining reliability. Food and water systems that can recycle and regenerate reduce the mass of consumables that must be carried. Everything redundant that can be made non-redundant is evaluated. Every kilogram of redundancy removed from one system could allow a kilogram of additional radiation shielding, or a kilogram of additional medical supplies, or a fraction more fuel. These are genuine trade-offs, not hypothetical ones. Interstellar vehicles face a situation where reaching them from Earth is impossible, which means the redundancy must be different in character, not simply more of the same system. Genuinely different approaches to the same function, so that multiple independent failure modes would have to occur simultaneously to cause a catastrophic loss. This philosophy makes each system heavier and more complex than a minimalist design would require. It adds mass. And mass is the thing the energy equations tax without mercy. Every engineering choice on an interstellar ship is a negotiation between the cost of failure and the cost of mass. And the cost of failure, at distances where no help can arrive, is absolute. The cost of mass is also, in its own way, absolute. There is no solution that makes the trade-off disappear. There is only the skill of making it as well as possible, given what you have to work with. There is one more physical constraint that doesn't get discussed as often as it should. As you accelerate toward a meaningful fraction of the speed of light, the kinetic energy your ship carries grows to scales that have no terrestrial analog. At 10% of light speed, a 1,000 kilogram spacecraft carries kinetic energy equivalent to roughly 108 megatons. That's not the fuel aboard the ship. That's just the motion itself, the kinetic energy of the mass already moving. A failure that causes a significant structural breakup at cruise velocity doesn't produce wreckage floating in space. It produces fragments, each of which carries enormous kinetic energy, continuing on approximately the same trajectory at approximately the same velocity. Managing this risk, designing for graceful degradation rather than catastrophic failure, ensuring that system failures cannot propagate in ways that cause structural breakup at velocity, is a constraint that doesn't exist for any other form of transportation. Humans have come and engineered. You validate the design through analysis and through testing of components and subsystems at accessible velocities. You then apply those validated models to the full-scale, full-velocity scenario. The safety margin for error is not generous. Now consider radiation. In interstellar space, far from Earth, far from any stellar magnetic field, far from any atmosphere, the radiation environment is constant and arrives from every direction simultaneously. The primary threat is galactic cosmic rays. High-energy particles, predominantly protons, but also heavier atomic nuclei, stripped of their electrons, accelerated to near light speed by violent astrophysical events scattered across the galaxy and beyond. Supernovae accelerate particles at their expanding